Hello everyone, good day, good afternoon, good evening, wherever you are. Today I want to dive into from monitoring to observability eBPF chaos. In the next 50 minutes we will hear the story around my learning story about eBPF, how to use tools based on eBPF and debugging certain things in production like an incident, and how chaos engineering and chaos can help with that. My name is Michael. I'm a senior developer evangelist at GitLab. I go as DNS Michi, which is DNS M-I-C-H-I on social media, on the internet, on Twitter, on LinkedIn, Mastodon, and on GitLab.com. So if you want to reach out to me, you can do so. Here's the resources actually. So if you want to follow along in this talk, you can access the slides using the QR code. I have my own newsletter. We will learn about certain many things. So it's key to remember them, even if you don't immediately understand them. Research, look into what is an eBPF program, what is a Berkeley packet filter. Diving into kernel user space, bytecode, compilers, C, C++, Go, and Rust might be related, and then going a little more high level with observability, DevSecOps, security, chaos experiments. Obviously a little bit of DNS will be involved, and then tying everything together with security chaos, eBPF probes, reliability, and more ideas which should inspire you to get more efficient with anything production related incidents and whatnot. So to get started with observability, so we had monitoring, now we have observability. How would someone define observability? And my personal definition of that is that I'm saying modern application development and deployment with microservices in using cloud native technologies that requires a new approach beyond traditional metrics monitoring or state-based monitoring. In essence, we are collecting a lot of data types, a lot of events, a lot of signals. So we are able to answer not the known questions, but what is the overall state of the production environment. But it's also key to identify unknown unknowns. So for example, a DNS response latency in a CI/CD pipeline actually caused the deployment costs to rise significantly. So the cloud costs are I don't know, 10,000 euros or dollars a month. And this is something you probably wouldn't figure out with the individual data sources and metrics on their own. But combined, this is what describes observability, and it's also a way to help reduce infrastructure costs. Now, considering that there are many different data types involved with observability, we started with metrics, then there were traces, logs, and events. Profiling comes to mind, error tracking, real user monitoring or end-to-end monitoring. Test reports even can be treated as observability data. And also NetFlow or network data, and there's much more which can add to the bigger picture within observability. And just to give you an idea what metrics are, it's a key value with tags stored in a time series database. Prometheus has become the defining the standard in the cloud native monitoring and observability community. It provides a query language, the open metric specification, which was also adopted into OpenTelemetry, and the ability to visualize that as a graph, doing forecast trends and whatnot. Now, there are different data sources within observability. So metrics from a Prometheus exporter, code instrumentation could be sending traces. Potentially in a Kubernetes cluster, there's a sidecar fetching the pod logs and then sending that to a central storage. And everything happens on the user level. And this is great to some degree, but sometimes we really want to look deeper. So there are more data sources, specifically a syscall, network events, resource access in a microservices cluster. This would need a deeper look into the kernel level. So we have more observability data possibilities even. Now, is the problem solved, or there is eBPF and everyone talks about it, it's on the kernel level, but what is it? What problem does it solve? And by definition, it provides observability, security, and networking at the kernel level, which the eBPF.io website describes pretty much. The thing is, the kernel needs to be stable, so there is like less innovation within the kernel itself. And the idea with eBPF was to run eBPF programs as an operating system runtime edition. So it's kind of an addition to the kernel, and you can like execute small programs in a safe environment. Looking into the use cases for these like small programs, one of them is high performance networking and load balancing, which is done by Cilium and others. You can trace applications, what they're like doing on the inside, which function calls are being executed. It also helps with performance troubleshooting. Different use cases come to mind with like fine-grained security observability, or even like something around application or container runtime security. So being able to see which network connections a container opens or something like that. This is all possible on the kernel level with an eBPF program when provided and developed. Now, an eBPF program itself is a little complicated to start with because the kernel expects bytecode, and nobody writes bytecode, so I have no idea how it looks like. And the thing is, we need an abstraction layer for that. So Cilium provides a Go library. There is like BCC as a tool chain. There's BPF trace. So a lot of tools and names floating around, which provide an abstraction layer in a higher level programming language, being able to like convert it and create bytecode for the kernel. This happens in a way that the verification happens with just-in-time compilation from bytecode to the machine-specific instruction set at the kernel level. So this is essentially in the background the idea behind it. From a user side, it's like, I need a lot to learn. This can be quite overwhelming, and for me personally, it took me quite some time to really say, okay, where should I be starting? Because there is like, what is the best learning strategy? I started my own research and documented everything on a knowledge base, which I maintain on o11y.love, which is linked in the slides. But in essence, at some point, everyone was saying, well, there's Brandon Gregg's tutorial, the blog post from 2019, but it's like, it's current, it's accurate. And it provides tutorial and examples for beginners, for intermediate and advanced users. And the best way to get started with is like start with a Linux virtual machine or on a Linux host. Use a kernel greater than 4.17, which provides access to eBPF support. And also on the way of like learning all these terms and tools and technologies, it's important like to note them. So when you don't really understand what it does, write the term down, and also like think about how would you explain what it does when you have like the first success moment in running BPF trace, and think about, hey, this solved my problem, but how would I explain this complex technology to others? And like doing so really helped me understand or even like verify my knowledge and considering, hey, I actually was wrong. So in essence, it's really a good thing to practice explaining this. And this is also why I'm doing this talk today. I got started with like looking into the BCC tool chain, which was mentioned quite often. And it's also mentioned in Brandon Gregg's tutorial. So I looked into what's available and what are the tools, and thought of, well, something similar to like strace telling me that a specific binary has been executed. So like exec-snoop -t means like trace a program or trace all programs which are actually like executing something or executing a binary. And in the first terminal, I ran the command. On the second terminal, I decided to run some curl commands just to like simulate an outgoing connection as well. Could be something like a malicious actor downloading something, which could be an interesting use case for later on. In essence, I saw something working. The commands have been logged. SSHD was also doing something. So I was like, okay, this is my first success moment, but like what else is out there? So I looked into the next tool or platform or framework, which was BPF Trace. So I was really like addicted to learning now, because BPF Trace provides many use cases or many things you can actually like probe or look at, and most obvious like Ethernet traffic, but also things like looking into file systems, and much more, like getting a better insight when high performance scaling systems are not working. And it provides a high level tracing language, so it's not like necessary to write deep down C code or something, but it's more inspired by dtrace and others, and it can help with ops and this retooling, maybe replacing even something like strace, because oftentimes it's really hard to remember what all the CLI tools are doing. So with BPF Trace, I thought, hey, there is OpenSnoop, which is able to trace open calls. And I thought, well, I could open a file by myself, but what if I write a quick C program, which just like opens a file, creates it, and then closes it again, in order to see or compile it and then see what OpenSnoop is actually doing. So I could write my own code and then see how the eBPF tooling is like handling that. So in essence, I made this happen, compiled the C binary, executed it, and then I saw not only that like the eBPF-chaos.txt was created, but also the libc was loaded by the binary. It was like, this actually makes sense, because the header include for the standard library is there, and libc provides that. So this was an interesting insight, also in a way of saying, I can verify what other files are being opened by this specific binary, and maybe see whether the call to malloc or JEmalloc or something else is actually happening. And well, it got me thinking, what else is out there? Folks have been mentioning like BCC, but this needs C and Python knowledge, or you should know at least like C on the side for the kernel instrumentation, and Python and Lua actually as a front end can be used to like run these programs. So BCC means BPF Compiler Collection. I found it pretty interesting because it's the first time I saw really like there's a hook into the kprobe sysclone, and whenever this kind of happened, it was printing the hello world command, and this really was like interesting for network performance, network traffic control and performance analysis and whatnot. It's like, okay, I'm bookmarking this now and documenting it now. What else do we have? Looking into libbpf, this got me interested as a C or Rust developer, because the great thing about it is there are bootstrap demos available in a separate repository, which also provided me with the term XDP, like measuring the ingress path of packets. And I was curious to like how would I be like compiling and installing this? Could be something like a TCP dump if I'm able to capture packets, but more in a faster and an efficient way. So I tried compiling the tools, tried several things, like is it the network interface name, is it the network interface ID, and after a while, I was able to actually see the packet size being captured and sent, for example, a systemd resolve process. And also I fired a curl command just to verify it's actually doing something. The slides provide all the instructions how to like compile that, and I've also linked a demo project at the end where everything is documented, so you can reproduce what I was doing back then. Now, considering that these are all great tools, what if I want to write my own eBPF program? So what is like the development steps to get going? And learning development is similar to like learning eBPF on its own, but I would recommend think about a use case which is either fun or which helps solve a production problem. So like think about an SRE or DevOps use case. Like a program is starting or exiting, there is like control groups, there are TCP sessions, network interfaces, something where you can easily see something or verify specific values or whatnot. Then it's required to select a compiler because there is like LLVM and even GCC in version 10, as far as I know, supports like compiling the eBPF program or the high-level code into an eBPF program within the bytecode, and we don't need to actually worry about anything like what is bytecode in the background. Now, for specific libraries, it's recommended to go Rust or C, C++ in the basics, or maybe I would say maybe probably intermediate or advanced knowledge is required to some degree. So all the libraries provide great examples on how to get started, documentation, but sometimes it's really like you should know the language to really understand what is the next step, or what is like the design pattern being used in the implementation. For once, I looked into the Cilium Go eBPF library, which was interesting because it also provided more use case examples. So actually like cloning the repository allowed to navigate into the examples path and then run the XTP measuring again. But in this case, for example, I saw that like it's storing the network traffic in so-called maps. So it's like a persistent storage within eBPF, being able to see, hey, this IP address was sending this many packets and so on. Now, there is more with the Cilium Go library. So like from the examples, you can attach to a program, the C groups, and again, like the network interfaces, which is a great way to start. For Rust, I've been looking into Aya-RS, which is a Rust developer toolchain. So like anything you know about Rust, you can just continue using it and use Cargo to build and even like run the examples. There is a book tutorial available online, which is fun to learn and look into. And for example, the XDP Hello program was sparking my interest again, just to see, hey, this is like how this example for measuring a network traffic is being implemented. The most interesting part for me was like in production, Parker is like a tool or an agent for continuous profiling from polar signals. And this is actually using Aya and eBPF for like magic function calls, stack unwinding and other things in different languages, using eBPF and using it in Rust because it's more memory safe, or there's better memory safety than like in raw C code, which is quite interesting. And the KubeCon Europe talk and all the slides and resources which are linked here are super interesting to learn as well. Now, considering that probably we don't want to like get started immediately with developing our own use cases and reinvent the wheel, because someone else actually thought about, hey, eBPF debugging and troubleshooting production, we should be building something, and people have been like looking into this already. I think it's important to like kind of separate or create an overview for different use cases. So considering that we think about observability, which is often the case in a distributed Kubernetes cluster or somewhere else, there is actually like a Prometheus exporter using eBPF. There are open telemetry collectors collecting metrics from different ways, which we will look into a bit. A different example is, for example, specifically for developers and auto instrumentation. When something is deployed in a Kubernetes cluster, Pixie is an example for that. More on the ops side, I found CoRoot, which has an interesting way of implementing service maps using eBPF and providing general Kubernetes observability. And last but not least, I've mentioned already Parker for continuous profiling. So these are like some tools. It's obviously not complete. So the ecosystem and community is growing fast in 2023, but it's important to like keep this in mind. Looking on the security end, on the security side, you can see like tools like Cilium for network connectivity, security and observability. Most recently, Tetragon was released for runtime security enforcement, specifically around like avoiding that an attacker can access a file or specific other things. Tracy on the other side also provides runtime security and forensics. We will see in a bit how to hunt the rootkit. And I think one of the most mature, or even I would say like the most mature tool is a Kubernetes threat engine or threat detection engine called Falco, which provides different use cases also to inspect what containers are doing. And the teams at GitLab have been inventing the package hunter, which does software dependency scanning using Falco just by installing a dependency in a container and then seeing whether it goes home or downloads some malicious software and whatnot. So it's pretty interesting space, and actually then knowing that eBPF is used in the background. Now, when we consider the third use case or the third area, I'm thinking of like for SRE and DevOps, what tools are out there, what could be helpful for eBPF. I found Inspector Gadget, which is a collection of eBPF-based gadgets to debug and inspect Kubernetes apps and resources. And there's a wide range of tools and things. So like trace outgoing connections, DNS, and even more. So it's like install it, try it out, and get to see what it's capable of. Another thought or another tool I found was Caretta. I think I pronounced it correctly. For instant Kubernetes service dependency maps, which also looks pretty awesome to get a visual picture of what is actually going on in the Kubernetes cluster. Last but not least, I was thinking of like, hey, an eBPF program needs to be distributed somehow. So like package it, tarball, zip file, whatever. And Bumblebee actually goes in the direction of building, running, and distributing eBPF programs using OCI images. So you actually like use a container image to distribute the eBPF programs, which is a nice isolated way and can also be tested and automated. Now, considering that this is all awesome, we also need to store all the events we are collecting. So changing the topic from like collecting the data or collecting the events to more like storage with all things observability. So we have so many different storage types over time. There is like a time series database, there's logs databases, traces databases, maybe an eBPF event database or something else like network traffic, NetFlow database, everything all together. Maybe it's time to create a unified observability data storage, which is something our teams are doing at GitLab, but also like others are doing that as well. So it's probably something to consider in the future. Now, for the storage itself, it's like what should be the best retention period. So how long do I need this data? Is now the incident that got resolved 3 days ago, do I really need to keep the data for future SLA reporting, or is it just good, well, for troubleshooting a live incident? Another question is like, do I really want to self-host everything and then like scale it and invest money to buy new hardware, buy new resources? Or would I be just uploading everything to a SaaS provider and then pay for the amount of traffic or data being pushed or pulled? Coming to the overall question, like which data do I really need to troubleshoot an incident, debug something? Also considering a way of like we want to become more efficient and also more cost efficient, we need sort of like capacity planning, forecasting, trending. The teams, there's 3 teams or infrastructure teams at GitLab have been creating Tamland, which provides that. It can also be used in a way of like estimating the storage needed by the observability systems by using observability metrics, which can be helpful to really like say, well, our growth of observability data is like a petabyte next year. Do we really need that data in order to reduce costs? Now, considering that observability also means like we're doing something with the data. We're defining alert thresholds, we have dashboards, we want to reduce the mean time to response. Because like an alert an alert is fired when a threshold is violated. So we want to do something about it, and obviously like also correlate, analyze, and suppress all these alerts, because when too many alerts are being fired, it's not fun debugging at 3 a.m. in the morning. And also, if there are new possibilities with eBPF event data, this would also be an interesting use case to actually add that. Now, considering that we also have dashboards, we need to like do something with the data. So creating summaries and correlations, providing the overall health state, reducing the mean time to response, and also considering like forecasted trends. The thing is, if the dashboard is green and everything is healthy, this doesn't prove anything. So all okay is like, how do I like verify reliability and all the tools and dashboards and whatnot? Which brings me to chaos engineering. So we can break things in a controlled way in order to verify service level objectives, alerts, and dashboards, and for that using chaos frameworks and experiments. The interesting thing is, like in the example before, that was chaos mesh, but there is like different chaos frameworks available, which is chaos toolkit, which can be run on the CLI, for example. Providing extensions with Pixie can be integrated in CI/CD. You can develop your own extensions. So it's like a wide variety of ensuring I can break things in my environment and then verify that all the data collection, which happens with eBPF also, is actually like in a good shape. Now, considering that chaos engineering isn't just like break things and then observability dashboards are read, but it's also a way of like thinking of going beyond traditional chaos engineering, injecting unexpected behavior, doing security testing, even like hardening software and doing some fuzz testing, which could also be seen or defined as a chaos experiment, which is helpful knowledge by looking into all the things which are helpful, because we will be talking about specific tools in the next few minutes, and we also want to break them to verify that they're actually working. And what are the weaknesses? What are like the edge cases which are not yet implemented and not yet solved? So let's consider some ideas and some use cases specifically tied to observability. So for like golden signals, it's rather easy to like create chaos experiments or use chaos experiments for latency, traffic, errors, and situation. There are tools and examples already available, so this can be verified. Considering that we might be using the eBPF to Prometheus exporter, we can collect metrics. The exporter uses libeBPF, supports core, which is like you compile it once and can literally run it with every kernel. So it's a good way to run it on different systems. I did it using a container, specifying in the box at the bottom with the command the different configuration names which are available, like using looking, for example, the TCP SYN backlog window and so on. So this is really like helpful to look inside. Thinking about like how to verify this is actually working. Add some chaos experiments, which is like CPU stress testing, IO stress testing, memory stress testing, adding TCP delays, maybe even doing a network attack or something in order to see that the metrics that are being collected with this exporter are not like all times the same, but you can like see the spikes, see the behavior of the system, and then also get an insight whether the tool is working or not. Now, looking into more like a different example, which I mentioned before, around like how developers can benefit from Kubernetes observability, where Pixie is one of the tools, provides auto instrumentation for a deployed application, and there's also a way to like get an insight with service maps, which can be a great way to visualize things. And it got me thinking of, hey, if there is like a service map, how does this change when there is an incident or when there's like something broken? So stress testing this again, or even like running a network attack to see if the service map changes, or to see if like the application inside the traces are taking longer. There might be some race conditions, some deadlocks, something weird going on, which could be a production incident, and then we can see, hey, the tool is actually working and providing the insight we actually need. And again, this is all using eBPF in the background. For Kubernetes troubleshooting, I've mentioned like there is Inspector Gadget, so we can trace DNS and even more within the Kubernetes cluster. It's not bound to Kubernetes only. There's also like a local CLI which can be run in a virtual machine on Linux, which is a great way to like get an insight. What are the DNS requests doing? Is there something like blocked, returning NX domain or something like that? And for chaos experiments, to like verifying that these tools are actually providing the expected results, like inject some DNS chaos, which provides like random results or NX domain results. Think about like breaking the network or doing even like a network DDoS attack, traffic attack, and out of memory kills, certain other things. Like this is really like a helpful tool chain, but in order to verify it's working, we need to break it. And this is why I'm always thinking of like test it with chaos experiments or chaos engineering. Speaking of which, for Kubernetes observability, it's also great to have service maps or getting an overview which container is like talking to another container, which co-root provides us with like the using eBPF for creating network service maps, which is a super interesting feature in my opinion, because it also provides an insight of like what is the traffic going on, the CPU usage on the nodes and so on. And if we break TCP connections or increase the network traffic, or even like stress the memory, how would this graph behaving? Or what is like the actual Kubernetes cluster doing? Which is a way to like also verify that the tool is actually providing the solution for our use cases. It's working reliably, and we can like use it in production in the future. And from time to time, again, run a chaos experiment to really verify that the tool is still working after an update or something like that. Yeah, lots of ideas, lots of things to consider when looking into profiling. And this is an example with Parker. Parker uses eBPF to auto-instrument the code, which means like function calls, stack debug symbol unwinding. I have to admit I know a little bit of this, but it's been quite a while I looked into it last. But it's really interesting that it's like auto instrumentation, and I as a developer don't need to take any action on adding this or understanding how perf calls work, which I cannot remember. The most interesting part here is like really that the agent provides all this functionality. There is a demo available, and the Polar Signals folks also started a learning series called Let's Profile, where they are actually like profiling Kubernetes and then looking into how to optimizing it, which can be a use case for your projects as well. But in essence, it's like continuous profiling is on the rise also in 2023. And the idea is how to verify that it's like that the behavior is there, that we can like simulate a spike with code traces. The function calls are taking too long. We maybe want to unveil a race condition or a lock in the software. So we can run CPU memory stress tests to see, hey, the continuous profiling results are actually showing that this under CPU stress, everything is like behaving as expected, or maybe there it is not. So this is really like a runtime verification or using some chaos experiments with continuous profiling. Now, considering that OpenTelemetry moved beyond traces, also with like adding support for metrics, logs, and different other observability data types in the future, there is a project which implements eBPF in OpenTelemetry to collect low-level metrics directly from the kernel, from a Kubernetes cluster, or even like from a cloud collector, which I think AWS and GCP are currently supported. The idea really is to send that to a reducer, which I think is like an ingestor, allowing to modify the data or sanitize it, and then send it or then provide it either as a scrape target for the metrics in Prometheus, or send it to the OpenTelemetry collector, which then can forward the metrics and do more with that. Now again, in order to verify that the data collection is usable, add some chaos experiments when testing the tool. Think about like CPU memory and also network attacks to really see, oh, the data being collected is actually like something valid or something useful in this regard. Last but not least, I think DNS is my favorite topic. There is a thorough guide on DNS monitoring with eBPF, which has a lot of source code and examples to learn. And in essence, to test that again is like similar to, hey, let's break DNS, add some DNS chaos to the tests, which I think is always a great idea because it's always DNS as a problem, whether in a chaos experiment or in production. Now, I've talked a lot about observability chaos with eBPF. Now, let's add some security chaos, which is pretty interesting, especially because we want to verify security policies with everything like going on. So thinking about how to break things, we want to, for example, inject behavioral data that simulates privilege escalation. Or another idea could be like there is multi-tenancy with data separation, and we want to simulate an access to a sector of a data set we shouldn't have access to. Which brought me like to the idea of, hey, what are the tools out there like promising kind of all these things? And I read a lot about Tracy from Aquasecurity, which had some interesting features described in a blog post and also in a recording, saying it can detect syscall hooking. And in the beginning, I wasn't really sure what a syscall hook means, but then I read on and thought, hey, this is actually like a rootkit, which can be installed on Linux, and then it kind of hooks the syscall and overrides the kill command or the get dance command, which I think is for directory listing, or could like override any syscall in order to do anything malicious, or just read password credentials or do Bitcoin mining or whatever. So in essence, I was curious of saying, well, how can Tracy detect a rootkit? And this was the first time I actually installed a rootkit on a Linux virtual machine, so on a fresh Linux virtual machine, not on a production environment. And I was able to like inject the rootkit and then run Tracy with some like modifications to the container command shown in the box here, to really see, oh, there's actually a syscall being hooked. I mean, it's all written or hidden in the screenshot, but it shows something weird is going on in the system. I was like, okay, this proves to be useful. Now, considering that like I also wanted to test different tools, I looked into Cilium Tetragon, which provides its own abstraction layer and security policy domain-specific language. And I thought of, well, this could also be used for detecting a rootkit. So like simulating a rootkit as a chaos experiment, or like simulate file access that matched certain policies. And after running Tetragon in a container, I was able to also see what the rootkit was doing, because it provided me with the insight of, hey, there was like some strange binaries being created, which then run some commands which are calling home, opening a port, and yeah, some like fancy things. Potentially the virtual machine is like now compromised, and we shouldn't be using it. But it was really like an interesting use case. Now, this got me to the idea, could we do a chaos experiment which is like a rootkit simulation? So like something which hooks a syscall but does nothing. I'm not sure if this actually is possible, but it would be an interesting way to do some like red team pen testing in production, trying to verify that, for example, the policies with Tetragon and Tracy are actually working. So impersonating the attacker again. Installing a full routine in production is real unwanted chaos. You don't want to do that. Trust me. I deleted the virtual machine after like doing the demos or the ideas for this talk, and documented all the steps to do it again, which should be fine then. Now, considering that there is more to that, so what is like the idea behind combining eBPF with chaos engineering and verifying that everything is working? I also had the idea of around like, hey, we could be using eBPF on the kernel level to inject some chaos. So change a syscall, change the responses, modify a DNS request into a different response, maybe even access protected data and try to protect it. So like when I thought about this, I also saw my friend Jason Yee having like a similar idea, using eBPF to collect everything, and then also think about like how does this help our chaos engineering work in that regard. And there's also a great research paper, which I linked at the bottom, for maximizing error injection realism for chaos engineering system calls, which is called the FIBE project, which brings more ideas into that area. Thinking of a real-world example with Chaos Mesh and DNS Chaos, it's using a plugin that implements the Kubernetes DNS-based service discovery spec, and it needs core DNS. So what if we could be like changing that eBPF program that intercepts the DNS request and then does some chaos engineering? And while looking into this and researching a little bit, I found Express DNS as an experimental DNS server, which is written in BPF, which has a user space application where you can like add DNS records or modify DNS records into a BPF map, which is then read directly by the module or by the eBPF program. And I thought, this would be actually an interesting way to do chaos engineering 2.0, something like that, to being able to modify DNS requests on the fly, and adding some high performance DNS chaos engineering to production environments. Now, another idea around this was like eBPF probes, something I thought of. This could be a feasible term for a chaos experiment. We can simulate the rootkit behavior in such small programs or snippets. Could either use a feature flag or whatever we want to use for like enabling a specific chaos experiment. We can simulate a call home using some like HTTP requests or whatnot. Could intercept the traffic and cause delays. So like I'm reading something from the buffer, I'm sleeping for 10 seconds and then I'm continuing maybe. Also considering CPU stress testing, DNS chaos, all the things which can be broken or which you want to break in a professional way and then verify reliability. Now, this is all great ideas, but we also got work to do. So vice versa, chaos with eBPF. Because from like a development perspective or DevSecOps, eBPF programs, this is like normal source code. You want to compile it, you want to run it, you want to build it, you want to test it. You want to look into code quality. So it's complicated to write good eBPF program code. It's also like humans make mistakes, so we need security scanning in the CI/CD pipeline or like shifting left. And we also want to see like if there are programs that could be like slowing down the kernel or could be doing something which is not with good intentions, like supply chain attacks, installing an eBPF program and magically it becomes a Bitcoin miner. So this is an interesting like problem to solve, because at the moment the kernel verifies eBPF programs at load time and rejects anything which is deemed unsafe. So in CI/CD, this is a nightmare to test because you need something to being able to test it, and you cannot really like run run it in actual kernel. So one of the attempts is like to create a harness which moves the eBPF verifier outside of the running kernel. And the linked article is an interesting read. Let's see how far this goes in order to improve everything. Another thought is there are certain risks involved. So like eBPF is ruled on the kernel level. There are real-world exploits, rootkits, and vulnerabilities which are actually bypassing eBPF. Because there are also limitations of eBPF security enforcement, using different programming techniques, different like ring buffers and so on. So it's like a cat and mouse game with eBPF. My own wish list for eBPF would be like having sort of like a fiber or sleepable eBPF program in order to like sleep and continue at a later point. Also considering observe or monitor like eBPF programs that observe other eBPF programs for malicious behavior, or having it like out of the box in the kernel. Better developer experience, and also abstraction by platforms. There are all great resources to learn and read, which are linked there on the slide as well. Now, as a conclusion, like the recap and inspiration for your next projects, consider eBPF as a new way to collect observability data. It provides you with network insights, provides security, observability, and enforcement. Add chaos engineering to verify this observability data, verify the eBPF program behavior, and also consider integrating eBPF probes for chaos experiments, hopefully done by upstream in the future. We have moved from monitoring to observability. We have moved from traditional metrics monitoring to being able to correlate, verify, and observe. We need to like consider there is data ops coming. We want to use the observability data for ML ops and AI ops. In the future, we might be seeing all ops or like whatever ops. And also consider like the benefits. Like we have observability-driven development with auto instrumentation, so developers can focus on writing code and not something else. We can verify the reliability from an ops perspective with chaos engineering. And for the sec perspective, we hopefully get better cloud-native security defaults from everything we learn while using eBPF. To-dos, the eBPF program verification in CI/CD, the chaos experiments using new technology, and also more ready-to-use eBPF library abstractions would be something. Last but not least, consider these learning tips. Start in a virtual machine, use Ansible or Vagrant provisioning or something else, and share that with your teams. I did that in the project, which uses Ansible to install all the tools in a Ubuntu virtual machine. Consider taking a step back when you don't understand names or technologies. Take a note, read on. You don't need to understand everything which is eBPF. A general understanding can help you when like the data collection breaks or something else is going on and the tools are not working. This is helpful information to get a deeper insight into what's actually going on. And that's it. Thanks for listening. Thanks for tuning in. You can read more about the GitLab observability direction on the left-hand side. You can access the demo project where all the tools and all the scripts are located. The slides are linked again here. Here's my newsletter where I write everything I learn about eBPF, about observability and also chaos engineering. Yeah, and you can find me on social media. For questions, hit me up in public. I will be at QCon in person myself. Otherwise, meet you virtually and hopefully at future events all over the world. Thanks for listening and have a great day. Bye.